Okay, so I forget to show the videos on the group motion editing, so which you saw last time. So far as you can get the videos, so you have to see the video first. Maybe it's easy to understand. But sometimes they lack this kind of information. So you may not know which part is important and which is not. So in that case, so checking the paper is useful. So this is the last part of the paper, technical paper. You may find it with figure 10 or something like that. So anyway, so this kind of graph formation, deformation is a very key novel part of this paper. And other animation, other parts are not so interesting, not so new for the people. So this is described in the figure, I'm not so sure, 5 or 6, 3, or something like that. So if we have a time, maybe if we have 2 hours, maybe I can tell you the technical details of this paper. But probably it's much useful to let you know the reading skill, quick reading skills of the papers rather than understanding these specific papers of the C-graph. So that's why I'm going to move on to the second one in the second class. So if you want to really interested in understanding this paper, so I may help you after the class. But during the class, I want to move on to the next one. So they don't care about how to say. For example, in this paper, they don't care about the speed, processing speed. So this is not real time. Actually, they don't show anything about that. So they don't care about the speed. They don't care about the scalability. So they can handle this kind of very large number of the people. But in the paper, they don't mention about the scalability. So in that sense, probably the scalability, so adaptation for the many people, many crowds are not the crucial key, important key of not understanding. So the other things, the advantage of the paper. Okay, so before we move, we move to the second one, reading the second one with the new reading skill. Of course, if so far as we have the videos, we should see the video first. That's a good guess. So okay, let's roll the video. So it takes 5 minutes.
So much so, we refer to them as a new representation for the editing of video. We would like to edit video of 3D surfaces which move and change their shape over time. For example,
so we have a 6 minutes video.
Talking head, and add features such as the moustache, rouge on the cheeks, and pinkly eyebrows. Applying such edits using current video editing technologies is difficult because of the deformity.
So they are artificially added in the scene.
Because of occlusion, the fact that each frame of video sees only a portion of the actor's face. Or we might take this video, A giraffe patrols the savannah, its neck undulating as the camera pans across the scene. Here the edits are rather unrealistic in order to demonstrate the technique. We add a symbol to the giraffe's cheek and a logo on its neck and flank.
You see,
Here we wanted to make the
mark
giraffe's
here.
neck shrink and expand.
So
Segmenting
shrink
the
and
layers is
expand.
an easy manual process, but where the neck shrinks, we need to fill in the newly revealed background pixels by copying pixels from other parts of the sequence. A hint at our new representation is given by this last task. Because the camera is panning, the motion of the background between any pair of frames is accurately modeled by a plane perspective transformation or homography, and it is easy to create a mosaic which represents the entire background at once. Editing the mosaic, for example by inserting some historic buildings and two tigers, re-rendering the mosaic with the original motion, and replacing the foreground layers, allows us to make modifications which apply to the entire video in one simple operation. For this task, mosaic creation was easy for two reasons. The camera's panning, and the background is, for the most part, rigid. Our paper shows how we can build mosaics from general to forming objects from general camera motion. We shall see later how the mosaic is computed, but let us first see how it is used for editing. Here we see the unwrapped mosaic extracted from the face sequence we looked at earlier. An artist paints directly on the mosaic this edit layer of moustache, eyebrows and cheeks. Then we re-render the layer into the sequence using a warp field associated with the mosaic. Here we show the edit layer being emphasized because the edited mosaic is warped to match the motion of the original sequence.
So red on the cheek and
Now
broad.
let's look at the extraction of the mosaic from a video sequence. We begin as we might in computing a planar mosaic by focusing computation on interesting patches in each frame and tracking these patches from frame to frame. This gives us 2D trajectories, one per patch, which can be viewed as points in a high-dimensional vector space, one projection of which is visualized here. To discover the mosaic's coordinate system, we compute a nonlinear projection or embedding of this space into 2D. Positioning the source image patches at their embedded coordinates, we can already see the outline of a face. However, for editing, we wanted a dense mapping. To recover a dense mosaic, we discard the patches and use the 2D points to define a warp field between each input image and the mosaic. Inverse warping each input image generates a new sequence which is approximately registered into the mosaic coordinate system. Although the registration contains many errors, each mosaic pixel is represented in many frames, so that conventional panoramic stitching using graph cuts gives a seamless mosaic. It is a happy characteristic of our method that if the mosaic looks good, it is good, because we can now refine the original mapping by matching directly from the mosaic to each input image. For the giraffe, the extracted mosaic contains both the side and front of the head. Applying this edit layer creates the sequence we saw earlier. This sequence is a little harder, mainly due to blur. The boy is manually segmented from the background. Like the face, the inverse mapping is approximately registered, but contains some large errors. Unlike the face, however, stitching does not generate a perfect result, with the actor's right ear appearing doubled in the mosaic. We provide a simple user interface to repair such errors. The user scrubs through the registered sequence, finds a frame where the ear appears correctly, indicates the correct pixels,
So this is illegal.
and recomputes the stitching with the constraint that the indicated pixels are untouched. Again, applying garish paint effects, we re-render and view the composited sequence. At the limits of what we can do, this rotating toy has protruding arms and cylindrical topology. The mosaic represents the torso and legs reasonably well, but truncates the tail and arms. And the repetition of the right arm also shows that we have not currently implemented cylindrical topology for the embedding space. This sports sequence is complicated by the spray, by motion blur, and by the repeated texture on the wetsuit. The recovered mosaic does not include the actor's back, and contains 2 copies of his legs. We end with a few more examples of the technique in use. This cliff sequence shows that unwrapped mosaics can cope with zoom, and also that unwrapped mosaics might offer advantages even for tasks which traditional effects software handles well. Although the sequence would be hard for current systems based on planar mosaics, it would be an easy job for today's 3D animation and match moving packages. With unwrapped mosaics, however, the user interaction can be very much simplified.